You hear it every second of your life. From the deafening roar of a thunderclap to the gentle whisper of wind rustling through leaves, sound is a constant and fundamental part of our existence. It is far more than just noise. It is a manifestation of physics in motion, a silent orchestra of vibrations that shapes our perception of the world. But what exactly is sound? How does it travel from its source to our ears, shape the very fabric of our reality, and, in some cases, even break the barriers of its own speed? Today, we will embark on an exploration into the astounding physics of sound, from the tiniest, imperceptible vibrations that create it to the thunderous sonic booms that can shake the very sky above us. Chapter 1. What is sound? Sound, in its most basic form, is a mechanical wave. This means it is a disturbance, a vibration that propagates through a medium by transferring energy from one particle to another. Unlike light, which is an electromagnetic wave and can travel through the vacuum of space, sound requires a substance to carry it. This medium can be a gas like the air we breathe, a liquid like the water in our oceans, or a solid like the ground beneath our feet. Without a medium, there is only silence. This is why the vast emptiness of space is eerily quiet. There are no air molecules to transmit the vibrations of an exploding star or a colliding asteroid. The speed at which sound travels is entirely dependent on the properties of the medium it is passing through, specifically its density and elasticity. In the air at a standard temperature of around 20 degrees Celsius, sound moves at approximately 343 meters per second, or about 1,235 kilometers per hour. However, when it travels through a denser and more rigid medium, it moves significantly faster. In liquid water, sound can reach speeds of nearly 1,500 meters per second, and in a solid like steel, it can race along at an astonishing 6,000 meters per second. This difference in speed is due to the closer proximity of particles in liquids and solids, which allows the vibrational energy to be transferred more efficiently and rapidly from one particle to the next. Chapter 2. Frequency, Pitch, and Volume. The rich tapestry of sounds we experience is defined by several key properties, most notably frequency, pitch, and volume. Frequency refers to the number of vibrations or cycles that a sound wave completes in 1 second. It is measured in a unit called Hertz, abbreviated as Hz. A wave completing 10 cycles in a second has a frequency of 10 Hz. Our perception of this frequency is what we call pitch. A high-frequency sound wave results in a high-pitched sound, like the shrill note of a flute, while a low-frequency sound wave produces a low-pitched sound, like the deep rumble of a bass drum. The range of human hearing is typically between 20 Hz and 20,000 Hz, or 20 kHz. Sounds below this range are known as infrasound, and those above it are called ultrasound. While we cannot hear them, many animals can. Elephants, for instance, use low-frequency infrasound to communicate over vast distances, their calls traveling for miles through the ground and air. On the other end of the spectrum, bats and dolphins use high-frequency ultrasound for navigation and hunting. Volume, or loudness, is our perception of the sound wave's amplitude. The amplitude is the maximum displacement or distance moved by a point on a vibrating body or wave measured from its equilibrium position. In simpler terms, it is the intensity or power of the wave. A sound wave with a large amplitude carries more energy and is perceived as being louder, while a wave with a small amplitude is quieter. Loudness is measured in units called decibels, or dB. The decibel scale is logarithmic, which means that a small increase in the number of decibels represents a massive increase in sound intensity. For example, a 20 decibel sound is 10 times more intense than a 10 decibel sound, and a 30 decibel sound is 100 times more intense. A quiet whisper might be around 30 decibels, a normal conversation is about 60 decibels, and a rock concert can easily exceed 110 decibels. Prolonged exposure to sounds above 85 decibels can cause permanent hearing damage. as the intense vibrations can physically harm the delicate hair cells inside our inner ear that are responsible for converting sound waves into electrical signals for the brain. Chapter 3: Resonance, Echoes, and Sonic Booms. The interaction of sound waves with the environment and with other objects leads to a fascinating array of phenomena, including resonance, echoes, and sonic booms. Resonance is a powerful concept that occurs when an object is vibrated at its natural frequency. Every object, from a wine glass to a suspension bridge, has a set of frequencies at which it will vibrate most readily. If a sound wave with a frequency that matches an object's natural frequency strikes it, the object will begin to vibrate with a dramatically increasing amplitude. This is the principle behind a trained opera singer being able to shatter a crystal glass with their voice. By sustaining a note that precisely matches the glass's natural resonant frequency, the singer transfers enough energy to make the glass vibrate so violently that its structure fails and it shatters. This same principle, on a much grander scale, was responsible for the infamous collapse of the Tacoma Narrows Bridge in 1940. Sustained winds created an aerodynamic flutter that matched the bridge's natural frequency, leading to catastrophic oscillations that tore the structure apart. Echoes are a much more common and familiar phenomenon, resulting from the reflection of sound waves. When a sound wave encounters a hard, smooth surface, such as a canyon wall or the side of a large building, it bounces off in a predictable manner, much like a ball bouncing off a wall. If the reflecting surface is far enough away, the reflected sound will arrive back at the listener's ear with a noticeable delay after the original sound, creating a distinct echo. This delay allows our brain to perceive the original sound and the reflected sound as two separate events. The science of acoustics heavily relies on understanding and controlling these reflections to design spaces like concert halls and recording studios. In these environments, materials are carefully chosen and surfaces are angled to either absorb unwanted echoes or to diffuse and reflect sound in a way that creates a rich, clear, and immersive auditory experience for the audience. Perhaps the most dramatic auditory phenomenon is the sonic boom. This occurs when an object travels through the air faster than the speed of sound, a velocity known as Mach 1, as an object such as a supersonic jet approaches the speed of sound. The sound waves it generates in front of it cannot get out of the way fast enough and begin to compress and pile up, forming a single, highly concentrated shock wave. When the jet surpasses the sound barrier, this shock wave of compressed air molecules propagates outwards and is heard on the ground as a thunderous, explosive sound, the sonic boom. It is not a one-time event that happens only at the moment the barrier is broken. Rather, the aircraft continuously generates this shock wave as long as it is flying at supersonic speeds. The boom is experienced by an observer on the ground as the cone-shaped shock wave passes over them. This intense pressure change is not just heard. It can be powerful enough to rattle windows and, in some cases, even cause minor structural damage. Chapter 4: Sound in Technology and Nature. The principles of sound are not confined to the realm of theoretical physics. They are harnessed in countless ways in both technology and the natural world, revolutionizing how we interact with and understand our environment. In medicine, high-frequency ultrasound waves are used to create non-invasive images of the inside of the human body. By sending pulses of ultrasound into the body and measuring the echoes that reflect off of different tissues and organs, a computer can construct a detailed image, or sonogram. This technology is famously used to monitor the development of a fetus during pregnancy, but is also vital for diagnosing a wide range of medical conditions, from heart problems to tumors, without the need for surgery or exposure to ionizing radiation. In the maritime world, sonar, which stands for sound navigation and ranging, operates on a similar principle. Submarines and ships emit sound pulses into the water and analyze the returning echoes to map the ocean floor, detect underwater objects like other vessels or schools of fish, and navigate safely through treacherous waters. Nature itself perfected the use of sound for seeing long before humans did. Many animals have evolved a remarkable biological sonar system known as echolocation. Bats flying in complete darkness emit a continuous stream of high-frequency clicks and listen for the echoes that bounce off of their surroundings. By interpreting the timing, direction, and characteristics of these echoes, they can build a detailed, three-dimensional mental map of their environment, allowing them to navigate complex spaces and hunt for tiny insects with incredible precision. Similarly, dolphins and whales use echolocation to navigate the often murky depths of the ocean. Their sophisticated clicks and whistles allow them to see their world with sound, locating prey, avoiding obstacles, and communicating with one another over long distances. From the simple vibration of a guitar string to the complex symphony of echolocation, the physics of sound governs a vast and integral part of our universe. Sound isn't just heard, it's felt, measured, and mastered, a powerful and invisible force that continues to shape our world and our understanding of it.